I want to talk about that are kind of fun. So these are fun. I mean, they're just weird. Not weird. They're weird. Yeah. So there's estimating and doing inference about break dates. So you got a regression. It's got a break in it, right? And you want to estimate when the break was, right? So for this, we have to suppose that this break thing is a good way to model it, okay? And then we're going to estimate the time of the break, and of course, estimating anything is easy, but doing inference about it is harder, right? You can estimate something by just flipping a coin, but doing inference is a lot harder. So we'll talk about that, and so this is of course Jushan Bai's work and Bai and Perron and Koo and Perron and all that stuff. Papers that you've seen or you know the authors and stuff like that. So I want to talk about that, and the goal of this again is I'm going to work through this in the context of a really simple example, and the hope is so that you can see kind of what the key trick is. Okay, and I think if you see the key trick, you'll understand sort of when it might work and when it might not work, and then I'll show you some empirical stuff. Where I don't. Well, we'll see whether it worked or not. Okay, so then I'll talk a little bit about Markov switching models and two versions of those: some recurrent Markov switching models and non-recurrent Markov switching models, and we'll look at those, and there's one version of this that I really kind of like, and so I want to show you this because maybe you haven't seen it. And then I'm going to go back to these models with martingale time variation because they're really good tracking models, and they make sense for forecasting. But we really haven't talked about estimating. We talked about estimating the path, if you will, right, in this filtering stuff or signal extraction stuff. But we haven't talked about estimating any parameters. So I'll talk a little bit about. I'll talk about maximum likelihood estimates of some key parameters there, and there are a couple of problems that show up. One problem is like a unit MA root thing, and I'll show you that, and maybe draw a picture that maybe Jim drew yesterday, but I'm not sure, so you have to tell me. If he did, I'll use a different color, so it will appear to be new. And I'll talk a little bit about data augmentation as a method, so this sort of EM method is sort of old idea applied here to these kinds of models, which makes life very easy. I'll talk a little bit about time-varying parameters as nuisance parameters. So, suppose you got models where you got two sets of parameters. You got some time-varying guys, and you got some other guys, and you got some parameters that aren't time-varying, and you only care about the guys that aren't time-varying, but you got these time-varying things, and do you have to worry about the time-varying things if you don't care about them, except to the extent that they mess up your inference about the non-time-varying guys? And of course, the answer is going to be here is if it's not too time-varying, it's not too important, right? But you want to understand what not too time-varying is and not too important is, right? So that's what this will be. And then I'm actually not going to talk about this. I'll talk about this tomorrow. It shouldn't be in this slide. Okay. So the first set of things we're going to talk about are breaks, and so think about your favorite model, maybe a linear regression model or something else that has a break in it. And again, to make the notation as easy as possible, I'm going to be dealing with scalars and no x's in the regression. So because those needlessly complicate things for the kinds of points that I want to make. So yt is a constant, beta plus epsilon, and this constant undergoes a break at date tau, and the object of interest now is not going to be beta or delta. It's going to be when did the break occur, right? So there's been a volatility decline in the macroeconomy. When did it occur, right? And we'll model it like this, right? So think of these as variances or something, right? There's been a productivity slowdown or increase. When did that occur, right? So we're going to assume it occurred at some date, right? So there's a break, right? And so we're going to date this, okay? And it's going to be important later on to talk about a break date. So that's the date at which it occurred. You got a sample of size 200. The break occurred at observation 68, right? So that's tau, right? And the other thing is we're going to talk about the break date in terms of the fraction of the sample at which occurred. So observation 68 divided by 200, I guess that's 0.34. So the break occurred 34% of the way through my sample, okay? And I will probably needlessly, bounce back and forth between talking about estimating tau and pi, right, break date and break fraction. Of course, if you know the sample size, right, it's the same thing, right? Okay, we're going to think about estimating these by Gaussian maximum likelihood, these break dates, right, or break fractions, right? And of course, that's just least squares, right? So we're going to estimate these guys by least squares. Key references here, the paper that I liked when I started thinking about this is this RE stat paper by Jushan Bai. He's got some stuff earlier, but this I found very clear. The algebra is just tedious as can be. That's not Jushan's fault. It's just it's the subject matter. And then there's a really nice paper. There was this, you guys probably saw this. Several years ago, the Journal of Economic Perspectives did this sort of special issue in which they had, econometric articles, right, in which you could have no more than 3 equations. I wrote one of these, Jim Stock and I wrote one of these in which I think we only put in 1 equation on vector autoregressions, and Bruce Hansen wrote a nice one on structural change, and so that's really worth reading. Later, I'll when I talk about implementing this stuff, at least in the context of that, Bruce put together some software, which is probably still on his website, in which you could do this stuff really easily. So I found that software to be used. It's like Gauss stuff, and it's useful to look at because it helps to try and figure, right, when you're doing algebra, it's nice to have someone who's written a computer program too, because then you can look at the algebra and look at the computer program and see if you made any mistakes in your algebra, right, in this case. And so I found Bruce's programs really useful for that. Okay, so I'm going to try and skip most of the algebra that is in Jushan's paper. And yet, I'm going to try and work out the methods for doing inference about break dates. And there's one complicated calculation that Jushan does. There's many complicated calculations that Jushan does. One of them is this, okay? And I'm not going to do it. Okay? I'll tell you why it's got to be true. It has to be true. But here it is. Okay? So pi hat is the estimated fraction, estimated break fraction. Delta is how big the break was. Okay? And then what Jushan shows is pi hat, the fraction, converges to pi naught, the true break date. So this is my estimated break fraction. That's the true fraction. And the speed at which it converges depends on a couple of things. It depends on how much data you have. That's kind of familiar, right? And it also depends on how big the break was. Okay? So let's just sort of go down, right? So let's take this and, remember the break fraction is the break date divided by the sample size, right? So sample size times break fraction is break date, right? So this just says that if I look at my estimated break date minus the true break date, scale it by how big the break was, right? I get a non-degenerate random variable, a big OP of 1 random variable. So this guy's going to have some probability distribution. Okay? It's not going to collapse to 0, right? So this says, well, you can't consistently estimate the break date. Okay? Now, if you think about this for a couple seconds, you should sort of say, well, yeah, okay, that kind of makes sense, right? The precision of your estimated break date is going to kind of depend on how big delta is. Okay? And it turns out this probability distribution here, in general, is going to depend critically on what the distribution of those errors is. Okay, so you're kind of, like in general here, you're stuck, right? I mean, you know, if you know your errors happen to have some distribution and you know your break date is about this size, right, then you could think about doing inference here. But, you know, like we never know any of that, right? So, what we try and do is think about procedures, right, that might work, right, for a wide variety of probability distributions, and we try and use averages and things like that, you know, and use central limit kind of arguments, right, to come up with sort of robust ideas. So, you know, let me just draw a picture to show you what's going on here. And again, this is kind of obvious, but it's worth talking about. I think it's worth drawing. Okay, so let me draw a picture. Okay, so I guess I probably want T down here. T. Okay, and here's the data. I'm going to plot the data. Okay, and here's what the data look like. You can't see this in the back. Sorry. Just listen. Right? So it looks like that. Right? So where did the break occur? Well, you know, it like occurred around here. Okay? Because look, right? It kind of occurred around there. Okay, well, you know, so I'm just going to say this is all kind of just, you know, did it occur, is this a pre-break observation or a post-break observation, right? Is this a pre-break observation or a post-break observation? Well, you know, it might be kind of hard to tell, right? If I think about, right, what, going back here, right, it kind of depends on what, you know, what the behavior of epsilon is, right? If epsilon has got some sort of weird distribution, right, with, I don't know, a bunch of mass out here, right? There can be some big positive ones. Well, this guy kind of looks like it's in the second regime, but it was really just a draw from that little hump, right? And, you know, similarly for this, right? So you're kind of not going to be able to, you know, really pin down, do inference about this break date, right? Form confidence intervals about this break date, right? Unless you really kind of know what's going on here. Okay, so that's one point to make here. And that's important, right? The other point to make here is, you know, just the obvious point, kind of the precision of your estimated break date, if you will, is going to depend on how big it is, right? Well, you know, if I'd drawn these points and put this up here, the break was bigger, it'd be easier to see where the break is, right? If the break date gets smaller and smaller and smaller, it gets harder and harder to see where the break date is. Okay, so that's point one. Okay, point two is, well, people do inference about break dates. They do construct confidence intervals using some schemes. So I want to talk to you about what those schemes are. I guess we know that kind of in general, those schemes can't work, right? Because the break date inference is going to depend on the distribution of the epsilons, okay? So what some guys do is this. They say, let's imagine a situation in which, sometimes we, sometimes the breaks aren't really big, right? So sometimes the breaks aren't really big, right? This thing, a break occurred. Break occurred, you just look at the data and you say, gee, a break occurred, right? Often, right, the data are such that you say, a break probably occurred, right? But I can't be absolutely sure, right? I can't reject no break with probability 1, right? So the break isn't big enough to have power 1 in a test, right? I might only have power of, 0.8 or 0.9 or 0.5, right? So let's imagine, so the game that we're going to play here, the buy game, right, is to imagine breaks that aren't nearly this dramatic. Think about breaks that are kind of small, right? And then, right, you end up with, dots that kind of look like this, and I'm not good at drawing dots, and then dots that kind of look like that, right? And now where did that break occur? Well, what do you do? Well, you kind of average these guys, right? And then you kind of average these guys, and you say, well, this kind of average is a little different than that kind of average, so maybe it occurred here, but maybe I should have let this line go a little further and started this line a little later, right? The key thing now is the game we're playing here is we're playing a game with averages, right? Averages are your friend in econometrics, right? Because averages say you're going to use central limit. Averages are approximately normal, so you can think about using central limit theorems, right? And think about doing inference which is robust to particular probability distributions because you're going to average out these humps and you're going to get normal stuff. Okay, so that's the buy game. Okay, yeah.
Clear about sometimes we talked about breaks yesterday, but you're talking about there's a fundamental difference here between testing when it happened as opposed to if it happened. Is that right?
Yeah, exactly. So now it's going to happen, right? So I'm not testing did it happen. I want to know when it happened, right? And I want to construct a confidence interval for the break date, not the size of the break. Yesterday we were interested in constructing confidence intervals for the size of the break and asking whether there's zeros in there. If delta is equal to zeros in the confidence interval, then the fact that a break didn't occur is consistent with the data. Okay, so I lost my little thing here. Okay, so let me just go through here. Blah, blah, blah. Okay, I got it. Okay. Okay, and we're going to think about a situation in which this thing goes to infinity, right? So this guy's big, so this is like our normal scaling factor of the difference between an estimator and the truth. So we're going to have this guy getting big, right? And we're going to kind of try and think about what the probability distribution of this guy is, sort of generically by using some averages. So this guy's going to be big, but delta's got to be small, or else we run into this other problem. Okay? So t times delta squared is big, but delta's small, right? So delta has to be small, but not too small, or it would kill t. Okay? So this is a big number, that's a small number. Okay? So that's what this says. So blah blah t delta squared is big, but delta is small. Okay? So for our approximations, right? We do calculations to get approximations. I'm going to think about delta getting close to 0 as t gets large, right? But t times delta squared getting big, right? So that's the approximation that we're going to use. That's the, if you will, nesting we're going to use. Okay, now, here's what we're going to do. We're going to consider, again, least squares estimators, right? What are least squares estimators? Well, here's the sum of squared residuals, right? If I assume the break date is tau, the sum of squared residuals is, well, yt minus beta. That's what's going on in the first regime, right? So that's the sum of squared epsilons between time period 1 and time period tau. The sum of squared residuals between time period tau plus 1 and t is this, right? And the difference is that beta's changed, or the mean has changed from beta to beta plus delta. Okay? So that's the sum of squared residuals as a function of tau. And now what I'm going to do is I'm going to change tau, right? Make tau bigger and smaller, see how this thing changes, right? And then choose the tau that makes this guy as small as possible. Okay? So that's the least squares estimator. And what we're going to do is to study the behavior of this estimator, this minimizer of this function. What we're going to do is we're going to look at this function and see how this function behaves in the limit. So we're going to look at a limiting version of this function and then think about our tau, which is the minimizer of this thing, as behaving like the minimizer of the limiting function. And the minimizer of the limiting function is going to be nice and nice. Nice and nice. Okay? Okay, so that's the game we're playing. Okay? Here it is. Okay, so I added some more steps to the algebra here because Jim said I had this line and like 2 of these lines, and Jim said add more steps. So I did. Okay, so let's just look at this. Okay, and this is beautiful, by the way. Okay, so I'm going to do all of this. Again, the calculations I'm going to do, beta and delta aren't the issue here. It's tau, right? So I'm going to do all the calculations assuming we know beta and delta, right? That's another difference between what I'm doing and what Jushan does, right? Jushan does it right, but that leads to a lot more algebra, right? I'm just going to assume beta and delta are known. So we're only going to think about tau. Okay. So now let's think about this objective function. And I'm going to think about this objective function on one side of the true value of tau. So suppose we looked at this objective function for some arbitrary tau, which is too big. This is the true break date, and I'm looking after the true break date. Right? How does this objective function behave? Okay, so let's just go through the steps. And for those of you in the back, get your binoculars, right? I used to carry a little anyway, but okay, so this is what it is. Okay, so here's my sum of squares function that I had before, okay, as a function of tau. Now, tau is bigger than tau naught, so I'm going to break this up, right? So this guy has t goes from 1 to tau. That's t goes from 1 to tau naught, right? But it also has in it, I guess, t goes from tau naught up to t, and I have y minus beta squared, right? And I wrote that as y minus beta minus delta plus delta, right? So this guy and this guy is that guy. That's my extra line of algebra to make this completely transparent to you. Okay? And this is from t goes from tau plus 1 to t. Okay? Well, now look at this, right? What's this? This is t goes from 1 to tau naught, right? That's just epsilon, right? So that's epsilon t squared. This is t goes from tau plus 1 to t, right? Tau naught's less than tau, so these are just epsilons. I deviated this from the right mean. So these are all epsilons. Now here I kind of messed up because I looked at y minus beta, and I should be looking at y minus beta minus delta, right? So this is really epsilon t plus delta, right? From t goes from tau plus 1 up to tau, right? So that's what this is. Maybe this is another line of algebra I added to make life, right? So now just, right, do the arithmetic, right? And I get what? Well, I get the sum of squared epsilons from t goes from 1 to capital T, right? And then the interesting part, right, is kind of this part is the tau squared part, or excuse me, the delta squared part of this, right? And then this cross product. Okay? So all I did now is this next line, again, because I'm sort of schizophrenic about using tau or pi, right? I just wrote this in terms of pi, right? And pi times t is tau. Okay? So now what we want to do is take this function, right, and minimize it over pi, or tau, same thing. Okay? And this doesn't matter, right? This is just sum of squared epsilons. Okay? So let's think about minimizing this guy. Now again, we're thinking about the case in which tau is bigger than tau naught. I'll do the case in which tau is less than tau naught separately, and then we'll put them together. Okay? So this is only one side of the problem. So let's look at this part of the objective function. This doesn't matter for the objective function. Let's look at this part of the objective function. Okay, so I just repeated that part of the objective function. Okay, so I got rid of the sum of squared epsilons. Okay, this bit right here, let me call this something. I'm going to give that a name. I'm going to call it new. Okay, or whatever that thing is. Okay, and it looks like I've divided it by sigma squared, and that's just because I want these in standard deviation units. Okay? So I just divided it by sigma squared because it makes something nice in a few minutes. Okay, so now I'm going to rewrite this guy. Let me rewrite this guy in terms of this variable new. Okay? So what's this? Well, this is just new. So if you will, dividing by sigma squared is just scaled this, right? So it's not going to change the minimizer. Okay? So take this guy, so this is new, right? And then I have 2 times delta, but, I divided by sigma squared, so I really have delta over epsilon, right? And then I have these epsilons divided by sigma epsilon. So these guys are going to have variance 1. That's why I did this. Okay? Okay. So now we're going to look at this guy. Okay, now this is great. So this is kind of an objective function. Minimizing this with respect to tau is the same as minimizing it with respect to pi. Pi and nu are related like this. So this is the same as minimizing this with respect to nu. Okay? So this is the function that I want to minimize, right? I want to look at the argmin of this. Okay? That's going to help me think about inference in this case. Okay, now let's look at this. Now this is kind of looking good, right? Because what's this? This is kind of like an average, right? And averages are our friends, right? Because we're going to have normality going on. Okay? So, I guess when averages, when I apply a central limit theorem, a central limit theorem, right, can be applied when I have something like I add up epsilons over a whole bunch of observations, the sample size, right? And I divide by the square root of the sample size, right? So we kind of have to look at this, and I want to reinterpret this as the sum as t goes from 1 to sample size divided by 1 over the square root of sample size. So I just have to tell you what do I mean by sample size? Okay, so that's what this slide is. Okay, so remember delta is going to 0. Oh, this is nice. Delta is going to 0. So that must mean 1 over delta squared, for example, is going to infinity. Right? So what do we have up here? Well, I'm really averaging this over, well, how many observations? Well, t goes from 1 to, I guess, a whole bunch, right? 1 over delta squared times nu. Right? And then what do I have here? Well, I have delta. What's delta? Well, if 1 over delta squared is like sample size, delta is 1 over square root of sample size, right? So this is just the familiar calculation, right? This is just the familiar calculation. So this stuff right here is going to converge to, well, what? Well, I got 2, right? So there's the 2, right? And then this guy, right, is going to be our, if you will, like our normal, right? And, you know, this is 1 over square root of sample size. This is sample size, but times nu, right? So this guy is going to behave, that average bit is going to behave like this Wiener process evaluated at nu. Okay? And then what's the front of this is nu. Okay? So this function is going to behave like this function. Okay, so let me draw it. Let me draw it. Okay, how do I draw it? It looks like this. Here's 0. I'm going to draw it, probably not well. Here's g of this thing, nu. Okay? And I'm going to draw this for nu positive, right? Remember, I assumed tau is bigger than tau naught, pi is bigger than pi naught, nu's got to be positive, right? So let me draw this function. I'm going to draw this function in 2 bits, right? Let me draw this part of the function, right? "45-degree line," right? So that's nu, right? And now what am I going to add to it? Well, I need to add to it, right, this Wiener process, right? So what I have to add to it? I have to add to it something that looks like, well, I guess something that looks like that, right? That's this Wiener. So I take this, I add it to this, right? And so it kind of looks like something like that. Okay? So that's one side of the function. So this, I can really kind of, the black thing, you really can't see the black thing, right? You can only see that. Okay? And now what would I do? Well, we just did one side of this, right? Let me do the other side, right? And the other side's going to look just like this, right? The other side's going to have a 45-degree line going like this. Another Wiener process, which is going to be independent of this guy because it's going to have other epsilons going backwards, right? So there's going to be another guy here, right, that's going to be around some 45-degree line. Okay, so I could go like that or something like that, right? So, right, this is what, at the end of the day, what are we doing? At the end of the day, our estimate of nu is, well, the value of nu that makes this function as small as possible. For this particular realization of the Wiener process, right, I guess my estimate of nu is right here. That's nu hat, right? And then I convert that into an estimate of pi and an estimate of tau, right? So how can we think about this estimated break date in this situation? We think about this estimated break date as the minimizer of the sum of squared residuals function, right? But appropriately thought about, the sum of squared residual process can be represented like this. 2 45-degree lines, right? That's the deterministic bit, right? That are minimized at the true break date, right? Perturbed by noise. And the noise turns out to be this Wiener process on both sides. Okay? So if we want to think about what's the probability distribution of tau hat or pi hat or nu hat, I ask, how does the minimizer of a function like this behave? Okay? And so that is actually a well-studied problem references in by. Here's the function written out. And now I'm going to show you the quantiles of this function. Okay, so let's ask, what's the probability that the absolute value of nu, the true value of nu here, right, is 0, right? Because it's pi hat minus pi or whatever, right? So what's the probability that nu hat is less than some constant c? Let's find the c that makes this 50%, 67%, the usual, quantiles that we might be interested in if we were constructing a confidence interval or something. Well, here they are. I put them in. The only reason I put them in is because I wanted to compare them to this, right? So here are normal, right? The normal things is, plus or minus 1 for a standard normal. Plus or minus 1 gives us a 67% confidence interval. Plus or minus 2 gives us a 95% confidence interval. Now plus or minus 4 gives us a 67% confidence interval. Plus or minus 13 gives us a 95% confidence interval, right? So this guy really has tails, right? So as you go from a 67% confidence interval to a 95% confidence interval, the width of the confidence interval increases by a factor of 3 instead of 2. Okay, so this has some sort of, if you will, non-standard distribution, but now you understand it. Okay. So now we're done, right? Because now, right, we think about, constructing a confidence interval, right? And, what would ingredients for the confidence interval be? Well, there will be, we got to construct this nu hat thing, right? And so what's the ingredients of the confidence interval? Well, I guess for a break date, I guess I need to know the sample size, sigma epsilon, remember I divided by that, delta, and my estimated break date, fraction or date, right? And from the table, we know, right, here's a quantile 4.4, that's that number, 67%, right? So I know the probability that nu hat's less than 4.4 is 67%, right? A 67% confidence interval. If I wanted a 95% confidence interval, instead of using 4.4, I'd put in 13.8, right? Here's my nu hat, if you will. This is just that, right? Stick it in, solve it so you get pi in the middle as usual, right? Multiply through by t, so it's in terms of tau, right? And you get this, right? So this is a 67% confidence interval for tau based on tau hat and the other estimated parameters. Again, if I wanted a 95% confidence interval, it'd be 3 times as wide. Okay. Programs, I said Bruce Hansen's webpage, right? And they're very terse, and that makes them good because you have to understand I'm saying this to myself because I did this. The first time I decided to program this, I was sure I didn't understand the algebra or the programming, so I sat with Jushan Bai, Bruce Hansen, read algebra, looked at his code, and then when they coalesced, right, I thought that maybe I had understood it. Okay, so that's useful for me. Okay, so let me show you an example, and I want to be critical of this example. It's in this Stock Watson macro annual paper. So I thought I would throw this in here. And then I wrote down the numbers, and anyway, let's just go through it. Okay, so blah, blah, blah. I forget. It's the same example we looked at last time. Okay, so when we looked at last time, we said, what if I want to look at stochastic volatility in GDP? Let's estimate the stochastic volatility. G, it kind of wandered, and G, it kind of came down. Okay, so another model might be there was a break in the volatility, right? So let's ask G, if we take this break step function thing seriously, right, where did the break occur, right? As we saw before, it looked like it kind of occurred in early 1980s, right? But you do buy stuff, right? So this paper does buy stuff. And, it's, I guess the only wrinkle here is now we're talking about, I had a break date and a mean before, right? I had a break date and a mean, so just so we're not... Right, I thought about a break in this, right? And now I'm talking about a break in variance, right? But, right, if I think about, if you will, the error term in this equation is something that I could observe, which I could if I could estimate this stuff, right? Then a break date in the variance just says take this residual, this error, square it, right? The expected value of the error term squared is the variance. So this is the error term squared. This is its expected value of the variance. This is the deviation of the variance from its expected value. So you can apply the same mechanical stuff here. Okay? It looked as if, now this is interesting, it looked as if when we did testing here, it looked as if there was little change in the mean coefficients, right? But it looked like there was strong evidence of a break in variance. And of course, you could see that in the data, right? It just sort of, you could see it in the data. It was kind of clear there was a break in variance. Okay. Now, and the estimated break data, as it turned out, these were data from, went through 2000 or something, right? So based on those data, the estimated break date was like 1983-2. This is quarterly data, right? Go through the mechanical procedure that I just outlined here, right? And construct a confidence interval. And it's here. Okay, so it's 1983-2 plus or minus it should be symmetric. No. Okay, it doesn't have to be symmetric. Okay, why? This is interesting. I didn't look at this before I got here. Okay, let's go back here. Come on. Okay, what did I have to do here, right? I had to divide by sigma epsilon, right, to get this to work. Okay? Okay. Now, suppose there's a break. Suppose I interpret this as error squared equals variance plus deviation of error squared times variance, right? Suppose the variance falls. The variance of the deviation of the square from the variance depends on the variance, right? So because this guy got smaller, the variance of this guy got smaller. Okay? And that means that going back here, it turns out for this particular example, this is kind of cool, that the sigma epsilon that you have to divide by because of this variance thing, a decrease in variance introduces heteroscedasticity here of a certain sort, right? And so you divide by different sigmas, right? And that's what makes this guy not symmetric. So these lines kind of go like that or something, right, when you form this confidence interval. So that's, I didn't realize that, but that's, I guess I realized it at some point when we wrote this paper. And it makes a lot of sense, doesn't it? Okay? Okay, but that was not the point I was trying to make. The point I was trying to make is this confidence interval seems really narrow. Okay, so what does that mean? You know, I think it means that this can't be based on much averaging, right? This must be based on data that at the end of the day kind of looked like in terms of variances. Oops, I'm sorry, just the opposite of that. The squared errors were big and then the squared errors got small, right? And so we're pretty sure when this break occurred. If you're pretty sure when the break occurred, then when you go through this by stuff, right, it means you couldn't have been doing much averaging, right? If you're not doing much averaging, right, then really this confidence interval, right, is probably kind of a poor approximation because you didn't do a bunch of the kind of averaging, right, that we were trying to do here. This break for this particular example probably is too big, right, for this by stuff to kind of make me feel good about it, right? This is sort of too tight, right? So, so do I really think this is a 67% confidence interval? Probably not. Again, that didn't occur to me until I put these in the slides and looked at it this morning. So I added this. You guys don't have this in your things. What do you think about this confidence interval? This is like an exam question, right? You put this on an exam, and what would students do? Jeez, what do I think about it, right? The paper's written by the guy, right, who wrote the exam, right? It's got to be good. You don't want to say, well, the guy's a bozo, right? Okay. Anyway, maybe I'll use this as an exam question next year. So I have to TiVo it out of this. Okay. Okay. So that's okay, so that's that. Okay, so that's this by stuff. Okay, so done. Right? Okay. So if any of you got, anyway, I really like this part of the lecture because this is really hard if you read Jushan's papers, right? And this is really easy if you do this, okay? So I feel like I earned my salary today. Maybe, anyway. Okay, now, you could take these models and you could do some stuff, right? You could, instead of one break, you could put in 2 or 3 or 4 or 5, right? And there's interesting work by Jushan and Pierre Perron on this. And I don't want to talk about it except to say that if you've got a sample of size 200 and you've got 5 breaks in it, thinking about these things is kind of, maybe that's not the right way to think about what happened. Right? There's a paper by Jushan, Robin Lumsdaine, and Jim Stock, which says, suppose you're looking not just at one series with a break, but suppose you're looking at 2 or 3 or 4 series and they all happen to break at the same time, like income and consumption, and there's a change in the income process, right? Or there's a productivity slowdown across a bunch of countries, or increase abroad, or inflation comes down, or a great moderation in a bunch of countries, right? Then, it's not too surprising that if you've got multiple observations on the break date, you can do better, and these confidence intervals will get more narrow, right? In proportion, if you will, to the number of series that you're looking at, right? So that's what this paper's about. And then you could put multiple breaks and multiple series together, and that's what this paper's about. Okay, now, breaks in historical. Okay, so the nice thing about the problem with breaks, right, is that it depends on sort of why you're doing your empirical analysis. If you're doing your empirical analysis for forecasting, or you're thinking about the future, right, having some sort of break in sample that you view as deterministic, can be kind of problematic, because then you sort of think about, well, after the break, the world is stable, but if there was a break, maybe there'll be another break, but then how do you think about another break? And, there's kind of all those kinds of problems, okay? So I want to now move to models in which we think about the breaks probabilistically, right, for those kinds of reasons. If you're just interested in doing some historical analysis, like this great moderation stuff, it looked like the variance fell. When did it fall? Right? Well, then maybe something like this, makes sense. Okay, so let's have a model with breaks in which it's probabilistic, right? The well-known model, right? Sort of Jim Hamilton's model, of course, is designed for this. It is, right? It's been used by a bunch of people in a bunch of different contexts. Okay, so Y has a mean and a variance. As I've written it here, both the mean and variance depend on state. The state can be 0, 1, right? So the mean can take on one value or another value. The variance can on one value or another value, right? And in this model, as you know, you bounce back and forth between these states. Okay? You could think about doing estimation and stuff like that using the kinds of filtering things that we talked about earlier. The little subtleties here that are just worth mentioning, right, is testing for Markov switching in this model is a little difficult, right? So you want to say, are things constant or is there switching, right? Well, again, you have this problem that if the null hypothesis is true, there's no switching. One way to think about that is the mean and variance in the two regimes is the same, right? Well, then you can't possibly know what the probability is for switching from state to state because it doesn't affect Y. So you've got sort of unidentified parameters here, right? But this sort of Andrews-Bloberger, right, approach where we didn't know the break date could be applied here, right? So you could think about doing that. You can do estimation of this model. Turns out to be pretty easy. One easy way is via sort of data augmentation or EM, and I'll talk about that in a few minutes. There are lots of extensions of this, right? And you've seen as many of them as I have. You can put in more states. You can make these P's functions of stuff, right? You can do what, there's like a million papers that change this in interesting ways. Okay? Okay. So what I want to note here, though, is that one thing that I don't like about this model, or that might not be useful for some kinds of things that I think about anyway, is the changes here are recurrent, right? So you go from, recession to expansion to recession to expansion, So for that, maybe it's okay, right? But, for this sort of volatility stuff, you went from high to low. Are you going to go back to high? Or are you going to go to lower, right? So do you really want to say I'm going to go back to where I was? If I change, I'm going back to where I was, right? So that's not me, right? You want to move forward, right? You don't want to live in the past, right? So this recurrent stuff is literally living in the past, right? If you change, you go back to having long hair and wearing bell bottoms. So that wasn't pretty, right? So what you might want, right, is a model which says if you change, you change. Maybe you go back to the past, and maybe you go forward. You change, right? And you can think about souping this model up like this. And here's a model that I really like that is kind of a version of that. So I just want to highlight this so that I think it's inspired by a paper that I read once by these guys. I actually refereed it, but don't tell them. But I really liked it by these guys. Okay, so these guys this was the problem, right? That they were. So what they did is they wrote down sort of a Markov switching thing, right? But there are going to be k states where k might be a number that they're going to estimate, as it turns out, right? And what you're going to do is, if you're in state 2, right, at date t, then you have two choices. At date t plus 1, you can stay in date 2, or you can move to state 3. You can't move back to state 1. If you're in state 3, you can move to state 4. Okay? So you're always moving forward. Okay? You're always moving to the next state. And then the question is, Well, one thing that's kind of interesting is state 3 a lot like state 1? That's Hamilton, right? Or is state 3 completely different, right? So what they want to do is characterize or have the model flexible enough to estimate, are the states really different from one another or not, right? And there are a couple of ways you might do that. So I wrote down a couple of ways here. They actually do it a little differently. They use some hierarchical Bayes methods, but they kind of have this flavor. Okay, so one thing you might do, and this is what they did. They said, in my simple model here, so let's just think about the mean. The mean's the only thing that's changing, right? They say, the mean in a given state is equal to an overall mean, right, plus something that makes us different. Okay? And the thing that makes this different is, in this case, a normal 0, sigma squared. Okay? So when you change state, this is what you do. You draw a new mu, or mu-st, right? And by estimating or changing the variance of this, right, you change how much you're changing and how much the new state is or isn't like previous states. So by seeing data in which it looks like you've changed states a few times, you can get an idea of, gee, when the states changed, how much did they change? Now, of course, to be able to estimate that precisely, you better have changed states quite a few times, right, so you can get an idea of this. Okay. Another thing you might do is you might say, now they didn't do this, but this might be sensible. You might say, gee, the mean in state 3 is a lot like the mean in state 2, right, plus a little increment, right? So anyway, this is, if I think about sort of forecasting and sort of adaptively, if you will, tracking something that's evolving through time, this model, this Pesseron, this guy, and Timmerman is a nicer way, I think, than this. This, of course, Jim's model is very useful for many things, but I like this better for many things. Okay, that's all I was going to say. Okay, so that's Markov switching. That's discrete breaks, but they're stochastic. Okay, now, next thing is other ways of incorporating time variation, and I want to think about it in forecasting models. Okay, and, what do real forecasters do? Right, or not real, I'm sorry. What do some real macro forecasters do, right? If you ask, Larry Meyer, how do you earn your salary, right? By forecasting, he would say, I have a model, and that's a model, and I have insight and judgment, right? So, right, what he will do is run his model and then look at the output and change it. Okay? That is, he'll, in the jargon, he'll add factor it, right? Or introduce some intercept shifts, right? So that's subjective judgment. In the context of these models, we might think of it as sort of an intercept or some time-varying coefficients that are evolving, right? And here's some differences in ways to think about it. Clements and Henry, I'm not going to talk about that. Interestingly, there's this old work that some of you may know by these famous econometricians who tried to formalize in a great way this sort of, add factor stuff, right? And what they did is basically considered or thought about this model. So this is the model that we've been talking about. We could interpret as the Cooley and Prescott adaptive regression model, right, from the early 1970s. Okay, so what they did is added an intercept to the model, which evolved smoothly as a martingale. Okay, so this is the thing, we've been dealing with, and then in their thing, there's some X betas, right? And so we're only talking about, if you will, the add factor part, right? The adaptive regression Cooley and Prescott bit. Okay, so I want to talk about some issues involved with estimation of this. Again, this is just a common filter model, so we've thought about estimating of the betas. To do that, what you'd need to do in this simple model, I guess there are only two parameters. You need to know the variance of that guy and the variance of that guy, right? And so, and I guess you need an initial value, right? So, so you want to estimate those, maybe by maximum likelihood or something. In this Gaussian case, probably would want to, well, anyway. So here's the, we know how to compute the likelihood function, right? And so then you maximize it. And it turns out you can easily concentrate out one of these parameters, this beta thing. You can concentrate it out by using a common smoother thing to give you the maximum likelihood estimator of that, conditional on these two guys. This is just turns out to be GLS. So this is where you can do GLS because your X regressor is 1, and 1 is strictly exogenous. Okay? So I remember yesterday I said I never saw a regression with a strictly exogenous regressor. 1 is okay. Okay, so this is an example. Okay, so now we want to maximize the likelihood with respect to those two parameters, sigma epsilon and sigma eta. And let me just talk about two problems. One problem is a problem that you run into when there isn't much time variation. So when there isn't much time variation, that is when the variance of this guy is small relative to the variance of this guy, it turns out that the maximum likelihood estimator is very poorly behaved. So I'll explain that. And so what you might want to do there is use a different estimator. And I'll talk about that because it's kind of related to some things Jim talked about yesterday, I think, but I wasn't there. And the other thing is there are versions of this model that Jim is going to talk about tomorrow in which you don't just have one Y and one beta, you got a whole bunch of them. So he's going to talk about models where with big N. So one of his models is going to look kind of like this, but there are going to be bunches of Ys and hence bunches of parameters to estimate, right? And the question is, in those models, right, how do you handle it, right? And just doing brute force, give this to a nonlinear maximizer, might not be the smartest idea, and there are some tricks you can use. So we'll talk about data augmentation as a trick. Okay, so first, let's think about what happens when this guy is small. Okay, so you can see the problem. Is going to come and sort of bite you in the rear end by considering something that you probably know from sort of basic time series models, from like Box-Jenkins stuff. Okay, so here it is. This model, difference y, I talked about this before. Difference y is different beta plus different epsilon. So that's eta plus this, right? And that is an MA1 because it's got autocovariances that disappear after 1. So you've got this model. Okay? Now, suppose the variance of eta is really small. Right? Well, that means E is basically epsilon. Right? Because this guy's small relative to this guy. Right? If E is basically epsilon, right? Well, what's the moving average coefficient theta? Well, apparently it's 1. Right? So if the variance of eta is very small, this is an MA1 with MA coefficient, which is really close to 1. Right? And there are, well-known, and I'll go through this quickly, right? There are well-known problems with estimating MA models, right, when you've got unit moving average roots, right? So this is just a slide that says that, so work through the algebra on your own. If you know it, you know it. If you don't, you don't. So, with MA models, let's think of the MA1 model, right? So I've got an MA1 model with MA coefficient of 1/2. Theta is equal to 1/2, right? There's another model that's non-fundamental, right? That's observationally equivalent, right? That has a moving average coefficient of 2, 1 over 1/2, right? So you can always take these moving average roots and flip them and find a model that is observationally equivalent, fits the data exactly as well, has the same autocovariances, has the same likelihood. Okay? So 1/2 and 2 are the same, 0.8 and 1 over 0.8 are the same, right? Now, as you get very close to 1, the likelihood, right, because on one side of 1, it's the same as on the other side of 1, right? The likelihood's going to be symmetric around 1, right? So that means that if you look at the likelihood function, since it's symmetric right there, it's got to have a derivative of 0. If it's got a derivative of 0, that means that 0's got to be like a local max or a local min, right? Okay. Now, imagine a true model in which theta is really close to 1. Well, then kind of, except for sampling error, right, the expected peak of the likelihood is at theta, but add a little noise, right, and you're going to get, that might hop over to 1, right? So this means that in models like this, there's a finite probability mass that the maximum likelihood estimator is going to be exactly 1, right? And as the true value of theta gets closer to 1, that probability gets higher and higher and higher. Okay, and this is studied in these papers. There's other papers as well. Okay, so that says in situations in which this guy's close to 0, you often find theta is equal to 1. Theta is equal to 1 is the same thing as saying sigma eta is equal to 0. That is, you will estimate no time variation even when the amount of time variation is there, but not very big. And it's not like you estimate 0.01 and it should be 0.03. You estimate 0. That's the thing. You run your thing and it says 0. And you go, damn, 0? 0, right? And it's because of this. It's 0. Right? You keep looking for more decimal places, but it's not. It's 0, right? So this is a problem with the maximum likelihood estimator. So, one can think about using different estimators here. And people have proposed different estimators. I'm going to talk about one that Jim and I proposed. And there are other ones here. I'm going to talk about this just because it fits in with some stuff that Jim talked about yesterday. Okay? So here's the idea. I have to draw this picture. And I don't know if I think Jim did something like it yesterday. When he talked about weak instruments, did he talk about median unbiased estimators? Inverting test statistics to get confidence sets? Okay, so that's what we're going to do here. I'm going to do it again, but in this other context. Okay, so this is what we're going to do. And I'm not going to go through algebra here. I'm just going to show you the idea. I'll write big for those of you in the back. Okay, and I want to estimate, let me call the parameter I want to estimate gamma, and that's going to be sigma eta over sigma epsilon. This is some notation I used yesterday actually in the same setting. Okay? So if gamma is small, right, the maximum likelihood estimators, that's gamma is 0, sigma eta is 0, right? So if gamma is small, we've got this pileup problem. So we'll often estimate by maximum likelihood gamma to be exactly equal to 0. Okay. So here's the strategy. We're going to use a strategy much like, I guess, Jim talked about yesterday, for example, probably in the context of Anderson-Rubin statistics or other statistics, right, in which we're going to, in this case, we're going to estimate, we're going to construct some statistic. So here's a statistic that's kind of interesting. Let's construct, this gamma is small. Okay? So let's construct, yesterday we talked about ways of testing whether gamma is equal to 0, right? And we had, I don't know, this test, a QLR test, and this test, and Chow tests, and Nybloom tests, and all of these tests. Okay? Let's just take one of them, right? Let's take the, generically, let's take this test. I always use that thing, right? So that's some test. Okay? Like the QLR test, the quant test, right? And so this is our test, testing whether that guy's equal to 0, right? And what did we do yesterday? Yesterday we showed that under the null, that is, if gamma is equal to 0, right, this guy converges to something, right? And we figured it out, right? And it's got some critical, we figured out it's quantiles, those were critical values for the test, right? So this guy converges to something, let's call it squiggle, right? And that guy has some probability distribution F. Okay? Well, now what we're going to do is we're going to modify this just slightly. Let's think about gamma as being small, right? And let's do this. Let's work out this probability distribution for any small value of gamma. We already did it for gamma is equal to 0, but let's do it for gamma being equal to another small number, not 0, just another small number. Well, then this guy's going to converge to something. It's going to depend on gamma, though, right? So maybe I should put a gamma down here, and this probability distribution is going to depend on gamma. Okay? Okay, now, so we're just about done, okay? Did Jim do this? You guys nodding your heads? Feel good about this? Okay, good, okay. So these guys are nodding their heads, okay? Guys in the back, you're nodding your heads? He's nodding his head, okay, all right, okay. Cameraman's got it, okay. There's two great econometricians in the back who have been taking notes. Okay, so this is what we're going to do. Let me do this. I'm going to use different notation up here because I've forgotten what I use. Okay, so here's this probability distribution. Let's do this. Let's maybe I will use the same notation. I got to use the same notation because I'm going to screw up. Blah, blah. Here we go. Okay. So I guess in the notes, this F thing I called A, right? So let's call it A. Okay, that's the CDF. Okay? The CDF, of course, is a function. It depends on where you evaluate it, right? Let's think about the median of the CDF. Okay, so let's find the value of x that makes the probability that squiggle is less than x to be equal to 0.5. Okay? That's going to depend on gamma, right? If I have different gammas, I have different probability distributions. So the median of the probability distribution is going to change as I change gamma. Okay? So let me put gamma down here, right? And let me draw this, well, here is gamma is equal to 0, right? Here's the median if gamma is equal to 0. I'll do it right there. So that's the median of the probability distribution of the test statistic under the null that we worked out yesterday. Okay? And now let's work out the distribution when gamma is equal to 0.1, small number. Statistic's going to have a median. The probability distribution is going to have a median. Let's work it out there. I'll plot it. Boom. Right? Gamma is equal to 0.2. Right? Boom. I'll put it like that. Okay, I'm drawing this so it's monotonic, as you noticed, right? And I'm going to do that for all these different values, right? So then you get some function that looks like that. Okay? So that's this median function, right? So this is this median function. Okay? So now, how are we going to form here's our estimator. Here's the estimator. Okay, this is very clever. Okay, this is very clever. This is what we're going to do. We're going to go out to our data. We're going to go out to our data, and we're going to compute this test statistic. We don't care if the null is true or not. We're just going to compute it because it's fun. Okay, so we're going to compute the test statistic, and then let me come over here, and here's the test. That's the value of the test statistic. Okay, and this is what my estimator of gamma is going to be. I'm going to go like this. Going to read over to the median function and then go down. Okay? Did Jim do this? Okay, great. Okay, this is value added then. Okay, now this is interesting, right? Here's a property of this estimator. With probability 0.5, the true value of gamma is bigger than this. With probability 0.5, the true value of gamma is less than this, right? This is a median unbiased estimator. Probability 0.5, it's too big. Probability 0.5, it's too small, right? Why is the probability the true value of gamma is bigger than at 0.5? Well, if the true value of gamma was up here, right, then I would have chosen, then with probability 0.5, I would have found a value bigger than this, right? And if it was less than this, with probability 0.5, I would have found a value less than this, right? So this turns out to be a median unbiased estimator, right, of this statistic. This guy turns out not to have a pile-up problem, turns out to perform much better in this situation. Okay? Now, Jim probably did this, but let me just finish this off, because this method, of course, can also be used to construct confidence intervals, right? Using whatever it is, the method of confidence bands, right? Did Jim talk about that? Yeah, okay, which looks like this. Instead of the median function, right, let me do this. Let me plot let me get rid of that. Let me plot the '95th quantile, right? And let me plot the 5th quantile. Okay? And then how do I construct a 90% confidence interval? Well, I go and compute my statistic, whatever it is here, and I read over like this, like that. And this value in here is my 90% confidence interval, because 5% of the time this guy's too small, right? This guy's too small, right? 5% of the time this guy's too big. Right? So this is a general way for constructing confidence intervals given one statistic, if you can compute its quantiles as a function of the parameter of interest. Right? So you see this applied right in this weak instrument stuff that Jim talked about yesterday. Right? You see this applied in a standard application of this is you want to construct a confidence interval for the largest autoregressive root, right? And you can't use normal approximations, right? So Jim has this old JME paper in which he does this, the method of confidence bands, to do that, right? So that's the way, that's a standard way that people do that. Okay, so that, I like this because this is like Statistics 101. Okay. And then here's some data, some stuff. I'm not going to talk about this because we're running out of time. I need to spread these. See, I had too much time this morning and now I'm running out of time. So clearly I'm not. I need to smush this stuff around. Okay, so I want to go to this other issue now. This other issue is estimating this model where you might have a large computational problems in large models. So I want to consider a version of this model where you've got many unknown parameters, not just sigma eta and sigma epsilon, but you've got like a zillion parameters, and you've got to do nonlinear maximization of the likelihood. Okay? And an example is something Jim's going to talk about tomorrow, right? A standard little factor model, right? So y is now a vector with n variables in it, right? This is an example of something I'll talk about. These y variables are pushed around by, let's say, one latent factor f, right? This capital lambdas, these are the factor loadings, right, are the coefficients relating the factors to the y's. These epsilons make these epsilons IID or something, or uncorrelated with one another. Let's let this factor evolve as an AR1. Okay? And now if you want to estimate this model, you got to estimate all of these standard deviations, all of the standard deviations of epsilon, standard deviation of eta. You got to estimate phi, right? And you got to estimate all of the lambdas. If n is big, like 200 or 300 or 400, right? This is a lot of parameters, and the question is, what do you do? Well, so an easy way to do it is, here's an example of data augmentation, this EM thing, which is to ask yourself, and it's always important to put a closed parentheses here, wouldn't this be easy if I could observe data on F, right? So the data augmentation method works well if the answer to the question, suppose I had data on blah, is then life would be easy, right? If that's the question and that's the answer, then what I'm going to tell you is going to help. So here, it's obvious if you had data on F, right, this would be really trivial to estimate. You'd regress each of the y's on the f's, right? You'd regress f on lagged f, and you'd call it a day, right? You'd go home. Okay, so that's what we're going to do. And so that's what this data augmentation EM thing. Here's a textbook treatment of this. There's this old paper by Paul Rood that I liked a lot when I read it. It's like Journal of Econometrics or something, because it's terse. Okay? And it's just like this page. And then a couple of theorems. It's just boom, and you get it. Okay? So here's the idea. You've got some observed data. You've got some unobserved data. This is going to be RY. This is going to be F. Okay? And, this is the likelihood for the observables that you care about, right? And you imagine, or you construct, you think about, what would the likelihood be if I could observe what I can't observe? That is, if I could observe the x's, right? So that's this. Okay. What you want to maximize is this. Okay. But here's the trick, right? Here's the trick. It turns out that what you're going to do is iteratively. This is what you're going to do. You're going to compute for some parameter value guess. So guess some parameter value. Theta naught. Compute the expected value of the likelihood from the complete data, conditional on the data that you have, using this parameter value. That likelihood, of course, is going to depend on theta, because it's a function of theta, right? And now what you're going to do is maximize this guy. When you maximize that guy, that gives you another value of theta. You're going to stick it in here and do this again, and you're going to iterate this thing, right? And then it turns out there are three nice results, right? Result one is that if you do this, somewhat surprisingly, the likelihood always goes up or never goes down. And number two, if this thing converges, it converges to, well, a local maximum. Hopefully that would be a global maximum, right? That's all you can hope of an optimizer, right? And in exponential families, think of them as normals in our case, right? This turns out to be even easier, right? So here's the game that you play in exponential families, right? This is what you do. I got to do this. Okay, so suppose you can do this. Write down the usual function which says, how do I go from the data, now the observed data and the unobserved data, to compute the maximum likelihood estimator? That's this function h, which is a function of some sufficient statistics. Okay, so how would I construct the MLE if I could observe these guys? Okay, so these are some sufficient statistics. Now compute the expected value of these sufficient statistics given the data that you observe. Apply the same function to them, right? And then that's an iteration. And then you take this guy, you stick it back in here, and you do it again. Okay, so let's just jump to this example so you can see it because it's so beautiful. It looks messy, but this is just regression. This is x prime x inverse x prime y, right? So if I could observe f, right, what's the formula for the maximum likelihood estimator of lambda? Well, it's just you regress y on f, right? What's the formula for the variance of epsilon? Well, it's just the usual, y prime y minus y prime x inverse x prime y thing, right? That's what that is, right? What's the maximum likelihood estimator of phi? Well, it's just that, right? What's the maximum likelihood of the estimator variance? It's just that, right? So these guys, all of these sample moments, right, are the sufficient statistics, right? This tells you how you map the sufficient statistics into your estimators, just regression 101, right? So now what do you have to do? All you have to do is find the expected value of all these sufficient statistics, right? And that, of course, turns out to be easy. The Kalman filter smoother tells you how to do that. You have to compute guys like, what's the expected value of y times f? Well, that's y times f, right? What's the expected value of f squared? Well, that's its mean squared plus its variance, right? Blah, 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 right? So the estimation procedure is really simple here. Guess some parameter values, run the Kalman smoother, compute these moments, take these moments, stick them into a regression package, boom, you get new estimates. Go back up here, do it again, right? And what's really nice about this, for those of you that have tried to write computer programs involving anything complicated, when you write a computer program involving anything complicated, you always make a mistake, right? You always make a mistake. And then you fix it and you make another mistake. You fix it, you make another mistake. And finally, you can't find any more mistakes and you think you're finished, right? But you really worry because you found lots of mistakes. And the only reason you're not finding another mistake is that you can't find another mistake, right? And what's very nice about this is you've got this little theorem, right, which says if you do this, the likelihood will always go up or not go down, right? So if you run this algorithm and along the way you compute the value of the likelihood and you see it fall, it means you made a mistake, right? And you need to fix it, and you need to find it, okay? And so it's like a wonderful debugging device. Okay. I'm not going to talk about that. Let me talk about, if I can have you for just 2 minutes. 2 minutes, okay? Because I have to show you one more thing, because this is kind of important. Okay. So here's the problem. here's the problem. You got a model, and it's got two sets of parameters in it. All models have two sets of parameters. The parameters that you care about, right? And then all of the other stuff you have to estimate to figure out the stuff that you care about, right? So the stuff that you don't care about that you have to estimate anyway, right, they're called nuisance parameters, right? And then there are the parameters of interest, the things you care about, okay? So let's suppose that you're in a world in which you've got some parameters of interest, call them theta 1, and then you've got some nuisance parameters theta 2, right? So maybe, an example from, this is Hong Lee, and this is a paper by Mueller and Lee, is, I forget what Hong was interested in. Maybe it was something like a new Keynesian Phillips curve or something, and it had some parameters in it, right? And she was estimating these using some VAR techniques, right? So there were some other parameters for the VAR, right? And her worry was, she'd sort of seen all this literature on VARs are always unstable. They have some time-varying coefficients in them, right? So she was worried that maybe using these VAR methods with potentially time-varying coefficients would mess up her inference about the parameters of interest, these coefficients in the new Keynesian Phillips curve. Okay, so that was the example. Okay, so what she did and what Ulrich and Ulrich Mueller and she did in two papers was sort of study this general problem, right? And let me tell you this general problem in the context of this example. Okay, so in the context of this example, suppose that beta is the parameter of interest and alpha is just a nuisance. Okay, so you don't care about the constant term, you care about the slope coefficient. Okay, just to make life easy. Okay, suppose the intercept term, the coefficient, the nuisance parameter has time variation in it, but beta doesn't, right? Does the fact that this guy's moving around like this mess up inference about beta? Okay, so that's the question. Okay, now it turns out you can do some calculations and you can see when it's a problem, when it's not a problem. So here's the idea, right? In this little regression thing, how do you estimate beta? Well, you deviate from mean, right? You deviate x's from means, right? You put the means in the constant term. You look at deviations from means and the x's, right? So that's all I've done here, deviated from means, right? Now, right, write out, so now these are all deviations from means. This new constant term, right, still has time variation in it because that bit's time varying, okay? Well, write out the OLS estimator. The OLS estimator for beta, which doesn't account for time variation, right, is just this, right? This is the usual formula for root t beta hat minus beta, right? Or beta hat minus beta is, x prime x inverse x prime epsilon, right? That's what that is, right? And then it's got this little contamination factor. Right, this is the part that comes from this time variation, right? And what Mueller and Lee do is ask when this part is small, when this part dominates, right? And it's pretty clear to sort of see what's going on. It turns out if the amount of time variation isn't too big, if this gamma isn't too big, right, then it turns out that this part is small relative to this part. Asymptotically, this part goes away in a sense. You can ignore it, right? And it turns out that this gamma, that this term is small in situations in which the power of this test isn't 1. If you were sure you could see time variation, then this is a problem. If you can't be sure you can see time variation, then it's not a problem, right? Now, if you could see time variation, it was really clear, what would you do? You'd fix it, right? If it's there but you kind of can't see it, well, then you worry about it. But these guys say, don't worry. You can't see it. If you're not sure it's there, no big deal, right? No big deal in that that term is small, that's the usual term, and you can do inference in the usual way. So this is really cool and kind of important stuff, right? So that's what the rest of this does. Okay.